Welcome, everyone! Today, we're going to explore the critical role of ammonia in shaping the future of our global energy system. Often overlooked, ammonia, with its simple chemical formula NH3, holds immense potential as a carrier of hydrogen, helping us bridge the gap towards a greener future. It's the invisible energy inside, ready to power our world, particularly in critical sectors like shipping, and ultimately drive the green energy transition forward. Pure hydrogen, while a powerful energy source, presents significant challenges for widespread adoption and transport. Firstly, it has a very low energy density, meaning you need vast volumes to store meaningful amounts of energy, which is inefficient. Secondly, liquefying hydrogen requires extreme temperatures, specifically near -253 degrees Celsius. This demands highly specialized, expensive infrastructure. Lastly, shipping hydrogen across oceans in its pure form, whether compressed or cryogenic, becomes incredibly complex, costly, and simply not practical for global trade on a large scale. This is where ammonia steps in as an elegant solution, truly hydrogen in disguise. An ammonia molecule consists of 3 hydrogen atoms bound to 1 nitrogen atom. Crucially, it liquefies at a much more manageable -33 degrees Celsius, vastly simpler than hydrogen. Ammonia is also already a globally traded commodity, meaning we have existing tanker fleets and port terminals capable of handling it. Furthermore, the Haber-Bosch process for producing ammonia has been proven and scaled for over a century. Ammonia truly acts as the vital bridge connecting renewable electricity to the global energy trade. Decarbonizing global shipping is an immense challenge, considering that 90% of all trade moves by sea. Batteries lack the energy density for long ocean voyages, and pure hydrogen is impractical due to its demanding cryogenic storage requirements for very large vessels. Ammonia, however, emerges as a promising pathway. It allows for liquid fuel storage and is rapidly becoming engine-ready for marine applications. International regulations are pushing for deep decarbonization, shipbuilders are developing ammonia-capable engines, and ports are actively studying bunkering solutions. The entire vision for ammonia in shipping hinges on the crucial factor: the cost of green hydrogen. Let's trace the journey of green ammonia, from its origin to its application as ship fuel. It all begins with renewable electricity, sourced from wind or solar power. This clean electricity then powers electrolyzers, which split water into hydrogen and oxygen. The resulting hydrogen is cleaned and purified, aiming for a target cost of $2 per kilogram or less. This green hydrogen then combines with nitrogen via the proven Haber-Bosch process to produce green ammonia. This green ammonia is then stored and exported, ready to power vessels, effectively ensuring that every ton of ammonia fuel ultimately traces its energy back to renewable electricity. The $2 per kilogram threshold for green hydrogen is absolutely critical. It's the cost parity target that will determine global viability. Several factors influence this price. Electricity prices are paramount, as 50 to 55 kilowatt hours are consumed per kilogram of hydrogen. High power bills directly translate to high hydrogen costs. Electrolyzer efficiency matters too. Better technology means more hydrogen per kilowatt hour. Utilization rates are key, as variable renewables can cause idle time, increasing the cost per kilogram produced. Finally, thin shipping margins mean even modest price differences significantly impact fuel choice. Above $4 to $5 per kilogram, green ammonia simply cannot compete without subsidies. Looking ahead, we face 2 distinct potential futures for green ammonia. In an optimistic scenario, renewable energy becomes abundant and cheap, electrolyzers scale efficiently, and hydrogen reaches that crucial $2 per kilogram target. Green ammonia then outcompetes fossil fuels, transforming trade routes into new energy corridors, with renewable-rich nations emerging as powerful new energy exporters. However, a pessimistic scenario sees renewables remaining expensive, electrolyzer scale-up stalling, and hydrogen prices staying high. In this case, ammonia struggles to compete on price, delaying its adoption in shipping and potentially stalling the entire hydrogen economy before it can truly gain scale. The success of green ammonia projects hinges on their ability to survive real-world system stress. Consider electricity volatility. Plants must operate economically even when power prices spike or generation dips. Intermittent renewables mean idle electrolyzers raise per kilogram costs, requiring careful balancing with storage or grid solutions. Policy and subsidy shifts can make or break projects dependent on incentives. Furthermore, new infrastructure layers like nitrogen separation, advanced Haber-Bosch reactors, and export terminals all add cost and risk. High utilization rates are critical for electrolyzer economics, and intermittency is the enemy. The truly successful ventures won't necessarily be the biggest, but those most resilient to these challenges. The rise of hydrogen and ammonia is fundamentally redrawing the global energy map, creating a new energy geography. On one side, we have potential hydrogen exporters, nations like Australia with abundant solar and wind, the Middle East and North Africa with high solar irradiance, and regions like Chile or Namibia with world-class wind resources. On the other side are key import markets. Japan and South Korea with limited renewables but high industrial demand, Germany and the Netherlands building major import infrastructure, China as the world's largest ammonia consumer, and the United States, with incentives spurring both domestic and import demand. Ammonia trade routes are poised to become the energy corridors of the 21st century. To summarize, remember this critical distinction. Ammonia carries the energy, but hydrogen is the energy. Our first key takeaway is that green hydrogen is absolutely paramount. All the promise of ammonia depends on renewable hydrogen reaching an affordable scale. Secondly, cost is the race. The $2 per kilogram threshold for hydrogen determines whether a low-carbon energy system is viable globally. And finally, geography is destiny. Nations blessed with cheap, abundant renewables will ultimately dominate the emerging hydrogen export economy. The success of green ammonia will ultimately be determined by the economics of green hydrogen itself. Thank you